Okay, we'll get started. This actually is going to wrap up chapter 4 today. This is the last activity that is specifically chapter 4. We're going to also continue on in the second half of class and begin chapter 5. Before I see you the next time, which means that will be after fall break, we do not have class on Monday, there will be another folder in Shobi. It will have inside of it a set of class notes, and it will have an individual code for a Nearpod that you can go to, or for either that or it will be, I may make a recording of the Nearpod, but I'll still give you the code because there's some quiz questions in Nearpod that I want you to complete and put your answers in the Nearpod as you're going through it. So just watch for that folder in Shobi, and it'll be due by the time I see you next time, so you need to finish it before Wednesday. But right now, we're going to talk about blood types. So what we have here is the data in a table that summarizes blood groups and RH types for 98 typical people. And the way the table works out, just so that you understand the table, this says that there were 35 people that had type O blood that were RH positive. RH is a factor in your blood, and people either have it or they don't. Okay? For example, I don't have it, but if your blood type is O positive, then you do have the RH factor. There were a total of 42 people that had type O blood. This is the 98 people that were in the entire group. 77 of the people had the RH factor, 21 of them do not. And these are the various totals for the blood types. We're going to use this table. It's called a contingency table or a two-way table. We're going to use this contingency table to answer some questions about probability. So the first question that we need to answer is, if one person was randomly selected from these 98 people, what's the probability that that person has blood group A? How many people in this whole group had type A blood? 39. So that was 39 people, probability of type A blood. 39 people out of the total, which is going to be that 98 people. Okay? So 39 out of 98. And we're going to go ahead and convert these into decimals and percentages so that we can understand better how likely that is. So that's 39.8% probability. And from that, if we could assume that that was a simple random sample of people, then we could say with some level of assurance that 39.8% or about 39.8% of all people have type A blood. Now our second question says the probability that a person has blood group O, given that they are RH positive. Okay, there are a lot of people that have type O blood. There's 42. But this statement right here is very, very important because it says, given that they are RH positive. The people that are Rh positive are the people in this row. So for that reason, there are only 77 people who have Rh positive blood. So that tells us then that the fraction for our probability is going to be 77, not the whole 98. And then we go back and we look to see how many of those people had blood group O. And that was 35. So 35 out of 77. And the way that you write that is the probability that they are type O, and this long line means given that they are Rh positive. Okay? And then again, we'll convert that into a percentage. So that's 45.5%. So if we're only going to talk about people that have the Rh factor in their blood, then about 45.5% of all people that are Rh positive will have type O blood. The next question asks us, what is the probability that a person is not type Rh? Well, not type Rh negative. If they are not Rh negative, it's okay. Tell me about it. I have them in bunches. Okay, if they're not type Rh negative, there's only one other possibility. They have to be Rh positive. This is actually an example of what in probability we call the complement rule. The complement rule says that if you have the percentage of people that do have something plus the percentage of people that don't have something, and we usually write that as a line over the top. So this is the probability of having type A plus the probability of not having type A. If you add those two together, you should come up with 100%, or 1. And the reason for that is because you can't have probabilities that add up to more than 100%. And that also tells you that if you know this, you can find this. So from that rule, we get a rule that says that you can find the probability of A if you take 1 minus the probability that you don't have type A. Or if you know the probability that you have type A, then you can subtract type A from 1 and find the probability you don't have it. And that's because the sum of all probabilities is 1. Or 100%. So this is really an excellent look at, what does the complement rule really say? This says the probability the person is not type Rh positive. If they're not type Rh negative, then they must be Rh positive. So the probability that they are Rh positive is 77 out of 98. which is 78.6%.
Do you want us to always run it as a percent?
I do, yes.
Okay.
Because I'm not really that good, and I bet most of y'all aren't either, at looking at a fraction that has really odd numerators and denominators and trying to decide, is that really likely or is it really unlikely?
Okay.
And if I put it in a percentage, you know, I know 10% is really low, 99% is really high, and I can figure out how likely something is. But I always want it as a percentage, and I always want it rounded to one decimal place. Always.
What do you see?
Sure. Let me actually move this off the top of the rest of it so I can kind of prop it up. You can see it better. Now, the other thing I want to point out to you, and this is the important part, this is the answer. And that is the right answer. But if you want to answer the question in terms of the way it was asked, it asked, what is the probability, and I'm going to scoot it back over here. What is the probability that they didn't have the RH factor? Well, that's supposed to be 78.6%. So if I actually count the people that weren't RH positive, I should still come up with the same thing that I got here. So if I go up here, the probability they were RH negative was 21 out of 98. So 21 divided by 98, and then take that answer and subtract it from 1. I should come up with the same number, and I did. So this is an illustration of this complement rule.
Can you scoot it over a little bit so I can see those three?
Okay? Now, does anybody have any questions so far? If I ask you about a lot of questions about probability on the test, you can expect to see at least one contingency table on your test when we do the test over probability. So you need to know how to read these tables. Let's go to another one. It says, what is the probability that the person has blood group blood group B, I can't read today, or is RH negative? Now, we're going to have to be really careful when we answer this question. Because when we answer this question, and I'm going to go to the clean copy of the table here and slide this up so we can see both at the same time. If I just look at this on the surface and I'm not careful, I say, okay, how many people had type B? Well, that's 7 people, right? And then how many people were RH negative? Well, that's 21 people. But the problem with what I just did, and it's not as obvious as it was yesterday when we tried this, is that if I count all the people that are type B and add it to all the people that are RH negative, who did I count twice? The one person who was both RH negative and type B. I can't count that person twice. So I have to subtract that person out to get the numerator of my fraction. So,
I'm sorry. Since it said, since you're saying you have to subtract that one person, if it ever comes like that on the test and it's like a different number, let's say it was 4, do we subtract 4?
you subtract the one that had both characteristics.
Okay, so it's
Or the
always be
ones
subtracted.
that had, yes.
Okay.
It's not just always subtract one, but subtract the number that had both characteristics that you're looking at,
Okay,
okay?
yes.
So in this case, we have 7 plus 21 is 28. 28 minus 1 is 27 out of the whole 98 people. So that will be 27.6%. And I'm still going to keep that little chart up here while we look at the next one. Because the next question says, what is the probability that a person has blood group AB and is Rh positive? Okay? That means I'm trying to count the people that have both characteristics. So for that answer, I've got to look at the people that are type AB and are Rh positive. And that turns out to be these 6 people right here. So that answer is going to be the 6 people that have both these characteristics. Out of the whole entire group, which is 98 people. And then if I change that to a percentage, I know that 6 out of 98 isn't very much, but I know that 6.1% is not very much either, and it's a lot clearer to me. And incidentally, be very careful when you're moving your decimal place. 0.061 is 6.1%. Because there were, let me go back up to this table and show you. Because it said that people that were both type AB and Rh positive, okay? So we go back up to the table, and we're looking at people that are AB, but we're also looking at people that are Rh positive, and it has to be that they're both. So these 6 people right here are both because they overlap.
Why did we put 7 over 98 in the last one?
Because the last one said or, it didn't say and. This one says or. So that means, let me see if I can clarify the language here a little bit better. Or means they are either B, or they are Rh negative, or they are both. Because a person that is both counts in both groups. But since we're talking about these people or these people, we can't count them in both groups till we count the total number. Does that make sense? So always think of or means either this one, or maybe both of them, and the both of them is what you have to take out, because you don't get to count them twice. But when we use the word and, that means they absolutely have both. This is why I told you you're going to have to read really, really, really carefully on the next test, because probability, you have to pay attention to the words. The words are very important. They have specific meanings. Now here's another given that. There's our table again. And this one says, if the person is Rh positive, or probability that the person is Rh positive, given that they have blood group A. So we're only looking at the people who fall into blood group A. We're really not interested in anybody else except the people that fall into this group. So of the people in that group, we're looking for the probability they're Rh positive. So that means we're looking for this 6 out of the total, or excuse me, not the 6. We're looking for this 30 out of the total of 39.
So is it gonna be in the end 30 or 30?
Mm-hmm.
Okay.
So this given tells you what the denominator of your fraction is going to be. Okay? So the probability that a person is Rh positive, given that their blood group A is 30 over 39, which is a pretty high probability, but we want to be a little more specific than that. So that's 76.9%. Which makes those kind of people fairly likely to occur. Now I want you to compare carefully this question with the next question. Because the next question says, find the probability the person is blood group A, given that they're Rh positive. So the given condition, the guarantee, is that they are Rh positive. Well, if we're looking at people that are Rh positive, we're looking at those 77 people right there. So they become the denominator, and then the numerator is the 30 people who are, and actually the way they write that blood type is A positive. They have type A blood and their factor is positive. So it's still this same 30 people that we're looking at. This 30 right here. Only now we're taking them out of the 77 that are Rh positive. So we're going to get a different probability. So that'll be 38.96. I could round that to 39.0%. That way I've still rounded properly, but the 6 says the 9 goes up 1, and if the 9 goes up 1, then 38 has to go up to 39. Okay?
When I did that, why would it be 35?
Where does the 35 come in?
The 35 comes in after, oh, I did that low, I'm sorry.
Okay, yeah, it's type A.
Okay,
And I put these next to each other here so that you would see the difference between the two.
yeah,
Okay?
okay,
The only thing that changes, we're still looking at Rh positive A people in both of these.
yeah,
But the difference is, which group are we comparing them to?
the RH.
Yeah, the A for this group and RH for this group.
Okay,
Okay, that's what, the only thing changes is the denominator.
okay.
Okay?
Yeah, I guess I was just.
Okay, now we got one more. This one's tricky, so don't let it catch you. The person has blood group O or blood group B. How many type O people do we have? Okay. How many people do we have that are type B?
7.
Are there any people that have both type O and type B blood? Are there any people that are both?
No.
No. If you've got type O blood, you got type O blood. If you have type B blood, you have type B blood. There is no combination of the two. So in that case, the or both means that you don't have any to subtract out there. So you don't have to worry about the subtraction part. So 42 plus 7 is 49. And this is out of the whole entire group, so that's over 98 people. And that actually turns out to be 50%. Exactly. That one comes out even. Okay? Now you have a practice to do with that to make sure that you understood it. I will post the answers before fall break starts so that you can do it and then check your answers. Once I post the answers, you can't do the worksheet. So you need to do that before the end of the week. Because I'm going to be posting the answers probably by Friday. Probably Friday night. Because I want y'all to go off on fall break without worrying about getting homework done. So I'm going to make you get this one done. Okay? Let's try another example now. This one works pretty much the same. See if I can shrink down the calculator a little bit. There we go. This one we have information about credit cards and whether or not people are employed or unemployed. So in the example we're looking at now, we have people that are employed, and there's 47 of them. And then we'll, of course, also have people that are not employed. Or unemployed. And there's 62 of them. And the total number of people that have been sampled are 109. And then they've been subdivided further into whether or not they have a credit card. So we have some that own a credit card, and there was 46 of those. And then we have some that don't own a credit card, and there's 63 of them. Now there are crossovers here. These 18 people have a credit card and they have a job. These 34 people don't have a credit card and they don't have a job. These 28 people have a credit card but they don't have a job. These 29 people have a job but no credit card. So as long as you can think your way through the table, you should be able to answer the probabilities pretty well. So the first question that we have, if one person is randomly selected, find the probability that the person has a credit card. What's the first probability they have a credit card? Okay, we're looking at the total number of people that have a credit card. And there's a total of 46 people that actually have one, out of the total of 109. So 46 out of 109 is a little less than half. And that'll be 42.2%. So then the next one is, what's the probability the person is unemployed? Well, we're talking about the unemployed people. So if we read across the table, there are 62 people who are unemployed. And that again is out of the total of 109. So that's 56.9%. Okay? Still analyzing the same information. The next probability is what's the probability that a person owns a credit card given that they're unemployed. So we're only looking at the unemployed people. And there are 62 unemployed people. Notice that when you're doing this, so there's 28 that have a card and are not employed out of 62 people not employed. Because unemployed and not employed being the same thing. So let's see what 28 out of 62 is. And that's 45.2%. So the meaning of that is that 42.5% of the people that were unemployed had a credit card. Any questions so far? Make sure you understand why the answers are what they are, because if you don't ask questions now, you're not going to know later.
Doesn't that mean that it's only gonna be the total of what it's looking at?
Yes, the total of that particular given thing.
Because when I read that, I always gonna think that, like, I thought that the next question was C was asking.
Okay, but the next question says they own a credit card, so we're looking at people that have a credit card. That's 46 people. Okay? So that's the thing to pay attention to. So this is a given. This means you know this for a fact. Okay? And if you're given that they own a credit card, you're only talking about that 46 people. And then the next question is unemployed. Well, out of just those people, just the people inside that box, 28 of those people are unemployed. So they're unemployed and they own the card. Okay? So notice the difference in the ordering of the letters. And it's always the one that comes after the line, after the given that tells you what your denominator is going to be. So the only thing that changed in my calculation then is that I don't need to divide by 62. I need to divide by 46. Which makes that considerably more people that if they've got a card, they're unemployed. That would be 60.9%. Is that clear to everybody? Does that work for everybody? Okay. Next question says, the person, probability the person is employed or they own a credit card. So that's the probability that they're either E or C. Now, are there any people that are both employed and own a credit card? Yes. How many are there? Okay. These 18 people, we have to be very careful, only get counted once. So there's 18 people that are E and C. So when we do this calculation, we need all the employed people, which is 47, And even though there are 46 people that own a credit card, 18 of those people have already been counted because they're employed. So we just very carefully subtract out those 18 people. So that's going to be 75 out of the total of 109. And again, that's going to be 68.8%. So there's 68.8% of the people that were in this group were either employed or they owned a credit card or both. And the key is not to get that mixed up with what the next question asks us. Because the next question says, unemployed and owns and does not own a credit card. So you can kind of think of these people as being the opposite of these. They don't have a job and they don't own a credit card. But that doesn't mean that this is the complement rule. You still have to consider they have to fit both these characteristics. So our unemployed people are in this row, and those that don't own a credit card are in that column. Let's slide that down a little bit more. So the people that we're looking for are the unemployed people who don't own a credit card. And there's 34 of those. I'm just going to write the complement of C because that means they don't own a credit card. So the probability they're unemployed and do not own a credit card is 34 out of 98, which is a little bit more than a third. Oh, I'm sorry, 109. I'm still on the last problem, thank you. So 34 out of 109. And that's 31.2%. Now you answer G for me. What's the probability that a person is employed?
Is it 18 over 109?
No, this is the probability of total number of employed people. How many people total are employed? 47. And it is out of 109, so that was good. But remember, the total of your employed people is this 47 people here. So that would be 43.1%. Probability the person is employed, so that's probability of E, Then we have a condition. Given that they own a credit card. How many people have a credit card? Total. 46. And out of those 46 people, how many of them have a job? 18. I think if you'll learn to kind of break it down that way, it'll make it easier for you to figure out how to do this. Okay, here's another given that. These are called conditional probabilities. Says the probability a person does not own a credit card. And you can write the complement as not C also. So does not own a credit card. Then we have a given condition. Given that they are employed. How many people do we have that are employed? Okay. And how many of those 47 people don't have a credit card? 29. So that's 61.7%. We've got our last question before we break and do something else. What's the probability that the person is unemployed given that they, oh wait, no, not given that, so I just about messed up. Probability they're unemployed or doesn't have a credit card. So unemployed or no card. How many unemployed people do we have? How many people do we have that don't have a card? Who did we count twice? So those are the ones that both were unemployed and had no credit card, so we can't count those twice. And then here again, we're talking about people that are out of the whole entire group, which is 109. Sorry about that. So 91 out of 109. And that's 83.5%. Okay? Now I want you to notice here, because this may catch you up sometimes, and this little hint here might keep you from making a mistake. If I hadn't paid attention to the fact that there were people that were in both categories, then my problem would have looked like this. 125 out of 109. Is that possible? No. You only got 109 people. You can't possibly have 125 out of that 109. Where are you going to get the other people from?
Well, that's when it gets there, it's like
When you're doing it, but now don't count on it. Yes, that's true, but don't count on it because notice I didn't bring it up until now. If you had done it here, you wouldn't have caught it. Because 47 plus 46 is 93, and you can divide 93 by 109 and got an answer, but it would have been wrong answer. Okay? But just be very, very aware that probability cannot exceed 100%. So I can't put down 114.6% for probability. Okay? Now you won't need to print anything out for this next thing. Does your bar chart look like mine? Would you be surprised if it did? You should be. Has the list made all the way around the room yet? Who's sitting on the list? Okay. Okay. So just read over these. I'm going to mention those briefly as we go through the rest of what we're going to do. The main thing I'm going to point out to you right now, because these are some common mistakes that people make. Mutually exclusive does not mean the same thing as statistically independent. They are totally separate. Mutually exclusive means something either happens or it doesn't. There is no overlap, okay? Either you drive a Ford or you drive a Chevrolet or something else, but you don't drive a Ford Chevy. That makes no sense, okay? So mutually exclusive is where things are totally separate. You can have the characteristic or not have it. And that's all there is to it. There is no overlap between the two. Statistically independent events are a little bit different from that. Statistically independent means that there is no relationship between the two. That the probability of one thing happening has absolutely no influence whatsoever on whether or not the other thing can happen. And a good example of that would be the temperature outside and what kind of precipitation we get. Temperature and precipitation are highly dependent events because, let's face it, if it's 80 degrees, it ain't going to snow, okay? And if it's 12 degrees, it might precipitate, but it's probably coming down as snow or freezing rain. Okay? So there is a relationship between the two. If I go home and I flip my light switch and the lights don't come on, and then I press the on button to my television and my television doesn't come on, those two events are not independent because they have a common cause. What might the common cause be? I don't have any power. Either I didn't pay my electric bill or somebody's took out a transformer somewhere around my house. Okay? So you have to think logically about those. The video that I'm going to post and the notes that I'm going to post for you to take while you're watching the video or going through the Nearpod, they give you lots of examples of statistically independent and dependent events. We're also going to talk a little bit about those here in a few minutes as we do this last part of the activity. So what I want you to do now, keeping all your M&Ms there in front of you, so that you can judge how likely and how not likely something is. I'm going to answer this based on my M&Ms, okay? This is based on my M&Ms. So I'm going to have to separate my hand out. You may want to separate yours. So that you can have your table to check as we go along. So my first question here says, suppose I reach into the bag that I had of my M&Ms and took out one M&M. What's the probability that that M&M was orange or blue? Now, I'm going to answer based on my bag. You need to answer based on yours. And I am going to grade these. We are going to take them up. That's why I had you send me around your numbers so that I can check your numbers to make sure you're understanding the probabilities. Okay? So, based on my bag, I have 14 orange and 15 blue. And I had a total of 56. So that's 29 out of 56. Make that calculator. And that means that there was a 51.8% probability that if I took out an M&M that it was either orange or it was blue. I didn't have to worry about overlap in this case because do I have any blue and orange M&Ms? Do you have any blue and orange M&Ms? No. So blue and orange are an example of mutually exclusive. The M&M was either orange or it was blue, but it couldn't be both. That's how you know something is mutually exclusive. If I were to reach into my bag, what's the probability the M&M I draw out is not brown? This is an example of the complement rule. Because an M&M, regardless of what actual color it is, an M&M is either brown or it's not brown. It's some other color. Now in this case, not brown encompasses the orange and the red and the blue and the yellow and the green. But the point was that it was not brown, okay? So if I look at my M&Ms, I see that I had 56 M&Ms, but only 5 of them were brown. How many does that mean weren't brown? 51. So I was pretty likely I'm not going to get brown one if I reach in that bag. That'd be 91.1%. And when I look at my,
51 on top?
hmm,
Those are the ones that aren't brown?
those are the ones that aren't brown. And if you look, and this is why I said hang on to your M&Ms, there's my brown M&Ms. Look how outnumbered they are. So I was really likely not to get a brown M&M. I was really likely to get some other color. That's the complement of brown. What's the probability that I draw out an M&M that is red and yellow? Now you answer this for you. What's the probability? 0. Because how many red and yellow M&Ms do you got? Remember, and means both. Do you have any red and yellow polka dotted M&Ms? Or red on one side and yellow on the other? Or red and yellow striped M&Ms? No. So you shouldn't even have to do any math to answer that. The key here is when it comes to answering probability problems and questions, don't park your brains. Common sense should tell you there's not any that are both of those. And the reason given here red and yellow are mutually exclusive. Can't be both. Okay? Cannot be both. Okay, another example of let's don't park your brains. If you reach into your bag and draw out an M&M, what's the probability it's white? 0. There are no white M&Ms. This one's not on here, but what if I ask you, what's the probability that you drew out a purple M&M?
0.
0. However, when I first started doing this activity, a great many years ago, there were purple M&Ms. Every bag had purple M&Ms in it. So they've changed their color configurations over the years. Now suppose you reach into your bag and you take out 2 M&Ms, one at a time, and you replace the first one before you draw out the second one. What's the probability that both of those M&Ms are red? Is there anybody in here that only has one red M&M? Anybody? Because your answer is easy. That was 0. Because you couldn't get 2. Well, actually, yes, you could actually get, because you put the first one back in. Now, if you got no red M&Ms, then this probability would be 0. Okay? Now, everybody else hopefully has at least 2 red M&Ms, or at least 1. So, what's the probability both of the times I draw out an M&M in my bag, what's the probability both of them are red? That means I've got to get a red one on the first draw, and then I've got to put it back, and then get a red one on the second draw as well. And if you remember, I told you that both implies the word and. That the red one and the second red one is and. It has to both be red. So red number 1, red number 2. If both of them are red, the rule says multiply the probabilities. That's only if you're working with a question like this. If you have a contingency table, you don't need to remember to multiply. The contingency table does that for you. But if you're working just from a bag of M&Ms, then yeah, you need to know the rule. It means multiply. So what's the probability of my first red M&M? Well, I didn't have very many red M&Ms. I only had 2. So the probability of my first one was red was 2 out of 56. Now if I put that M&M back and I draw out another one, then that means I still have a 2 out of 56 chance of that happening. That's where the given comes in. You don't have to have a rule for given probability. You have to think about what that probability is actually asking you for. You have to have the first one before you can have 2. So the probability of the first one was 2 out of 56. Probability of the second one is 2 out of 56. And that would be 4 out of 3136. So I can tell that's not really likely to happen. In fact, it's darn near impossible because it's only going to happen 0.1% of the time, at least in my bag. This is an example of an independent event. It's independent because I put the first one back in before I drew the second one. So my likelihood of getting the second one didn't change.
What if you didn't put the red one back?
Then that becomes what the next question asks. Okay? So this is independent. This one's going to be an example of dependent. This time, let's suppose I drew out the first M&M and I got a red one, so I ate it. Because I like red M&Ms. They taste better. Okay, if that happened, I'm still looking for red 2 given red 1. Sorry, that's backwards. So if I got the first one, there was a 2 out of 56 probability I got the first red one. What happens when I'm trying to get the second one?
2 out of 55.
How many red ones do I still have?
Oh,
1 out of 55. Very good. Because I ate the red one, so not only do I only have 1 red one left, but I only have 55 M&Ms left in my bag. So that's 2 out of 3,080. And this is going to be even less likely because I drastically reduced my second probability. Now that number, folks, is scientific notation. And if you write on your paper 6.49 and keep on going, or worse yet, 649.3, I'm going to mark it wrong and I'm not going to bat an eyelash because you know probability can't be 649 point something percent. You have to read all the way to the end. 6.49 yada 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 times 10 to the negative 6, or negative 4, I'm sorry. That E negative 4 means you need to move the decimal place 4 places to the left. One, two, three, four. Which means I need 3 zeros in there. And then that means that my probability then, if I write that as a percent, is 0.6%. Wait, 0.06. Six hundredths of 1%. Very, very small. Now, please be clear here. The reason that I moved 4 decimal places to the left was because of that. The reason I moved it back here is because I'm going from a decimal to a percent. So that's why the 0.06 and not, you don't leave it the other way. Okay? So way, way, way less than 1% chance. In fact, if I were to reach into that bag of M&Ms, how likely do you think it is I were to draw out those 2 in the middle? Probably not very likely, especially if I ate the first one before I put it back. Because then, not much chance at all for that one to get out of there. Okay? The idea here is for these to make sense to you. Now, in the next one, we're going to partially continue probability, but we're also going into the next chapter a little bit to get you prepared for it. So now we're going to divide the M&Ms into 2 groups. What we're going to do is I'm going to take away everything that's not brown or orange. You need to do the same. Put them back in the bag, eat them, whatever you want to do. We're keeping the orange ones and we're keeping the brown ones. So there's my orange ones and my brown ones. Now, I have 14 orange and 5 brown. Okay? What I need now to do is I need to write the probability that if I choose one M&M out of the bag, that it's orange. Is that going to be a high or a low probability based on mine? Which is more likely, orange or brown? Orange is way more likely. So there's 19 M&Ms on that plate and 14 of them are orange. So that's a 73.7% chance. It's pretty good odds. What's the probability now if I chose one M&M from the bag that my M&M is going to be brown? Not too good. 5 out of 19. Which is not impossible. I could do it. 26.3%. I wouldn't bet on this one, but I might bet on that one. What's the probability now if you choose one M&M from the bag that it's not orange? And that is the same as the answer to the last question, because if it's not orange, what color is it? Brown. Now this next one is going to go into Chapter 5 more. Chapter 5 is about probability distributions. And it's going to talk about something called a binomial experiment. We're not going to use rules to figure this out. I will show you after fall break how to calculate these probabilities with your calculator with a built-in formula so that you don't need to memorize this. What the question says, suppose you reach in the bag and I take a handful of 5 M&Ms out of the bag without looking. What's the probability the handful contains exactly 2 orange M&Ms? And does it matter if I choose all 5 at once, or if you take them out one at a time, assuming that you would put it back every time that you choose it? Would it make any difference? No. Because as long as I take all 5 at once, that's the same as taking out one, looking at it, put it back, take another one, look at it, put it back. And I'm not going to eat any of them as I take them out. Now this next question, y'all should know how to do, but it may intimidate you a little bit. This says, list here all the different ways you could draw out a handful of 5 M&Ms if you drew them one at a time. Now remember, there's only brown ones and orange ones in there. So what we're going to have now is a tree diagram. Which means I need to dig up my orange marker. So I'm going to take care of the fact it says that I need to have exactly 2 orange. Now the next question is going to be 3 orange and 2 brown, but we're going to list out all the different ways I could draw these M&Ms. One of the things I could get would have been all orange, or I could get all brown, because I do have 5 of them. Or I could get 2 orange and 3 brown, or 3 orange and 2 brown, or 1 orange and 4 brown, or 1 brown and 4 orange. Okay, a lot of different possibilities, but how many ways could I select those handfuls? That's where the tree diagram comes in. So we're talking about M&M number 1. M&M number 1 is either orange or brown. Then M&M number 2 is also either orange or brown. So here's my first M&M and my second M&M. Now from each one of those, I choose my third one. And it's either orange or brown. Then I pick again. And the first one might be orange. I have to get rid of some of those. And now I've still got to pick one more, because this was my first one. There's my second one, here's my third one, and now this was my fourth one, so I've still got to go one more time. So my last pick is either orange, or it's brown. Now, the advantage to the tree diagram is that I can actually list out every single possible handful. But I know that there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32 different handfuls. And they all look different. The top one is all orange. The bottom one, brown, 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 is all brown. This would be 4 orange and 1 brown. This one would be 1, 2, 3 orange, a brown one, and then an orange. So that's still 4 orange and 1 brown. This one would be orange, orange, brown, orange, orange. So still 1 brown, 4 orange. So there's 1, 2, 3, 4, 5 of them. This one would be orange, orange, brown, orange, brown. So that would be 2 browns, finally. And 3 orange. And then this one going backwards, orange, orange, brown, brown, orange. So that's 3 orange and 2 brown. That'd be 3 brown and 2 orange. This one would be 1, 2, 3, 4 oranges and a brown one. So that will be another one of those. This would be 1 orange, or 1 brown, and 3 orange. So that will be another 2 orange and 3 browns. This would be orange, brown, orange. So that's 3 orange, 2 browns. And that would take care of that one. And then this one would be brown, orange. So that will be another 2 orange and 3 brown. Orange, brown, orange. That'd be another one of those. So let's see, down here I need the ones I'm looking for in the next question actually is 3 orange and 2 brown. So I'm looking for this one. So, nope. 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 No. 3 orange, 2 brown. Okay, that's 3 orange, 2 brown. No. Yes. 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 And that's a no. So I have 1, 2, 3, 4, 5, 6, if I counted right. So 6 out of the 32 possible handfuls would have the combination I'm looking for. Now I'm going to let you double check yours. I'm going to let you keep it. Double check yours. Upload it into Shobi. Take a picture of it because I didn't put the document in there for you. So just upload it into Shobi with a picture when you get finished with it. And I'll have those checked before we get back at fall break because we only got about 5 minutes left. I want to let you have a little bit of time to get your stuff together. We will come back and finish this problem after fall break. Okay? This is going to take us a little longer than 5 minutes. I'll make a folder for this one in Shobi so you can upload it.